We're going to get started with Lecture 8, Giant Molecules. This is just a continuation of our unit under chemical bonding. So we're going to take a break from organic chemistry for a moment and look at these molecules that we refer as giant molecules. Alright, the essential questions for this lecture are: what are giant molecules? What are allotropes? And what is the silicon crystal structure? Okay, so we're going to start out looking at these giant molecules. Another name for these giant molecules are known as covalent network solids. I will use that terminology quite a bit, these covalent networks compounds. What they are is these are molecules made out of nonmetals. They bond together with strong covalent bonds that form these very massive or giant three-dimensional continuous structures that are crystalline. And so that's why we call them covalent networks, is they're covalently bonded together and they form a crystal network and resulting in a solid structure. What I would really take away from this lecture is that these covalent network compounds form very super strong covalent bonds. And because they form those strong or super strong covalent bonds, they have very high melting points and very hard solids. And we'll give you some examples of that as we go through this lecture. Alright, another word we want to introduce besides covalent network is this word called allotropes. Here's a definition of allotropes that you can write down. Allotropes are different forms of an element in the same physical state. So for instance, we're going to look at carbon. And carbon has 3 allotropes. It actually has more than 3, but you are only required to know these 3 allotropes of carbon. All of these carbon allotropes are solids at room temperature, so therefore they're considered allotropes. So they have to be the same element and they have to be in the same state, but they are just different structures because they're bonded a little bit differently. And we're going to talk about how each one of these allotropes of carbon are bonded. The first one there is graphite, and then we have diamond, and then we have what is called a fluorine ring or Buckminster ball. All right. I think graphite you're somewhat familiar with. We usually find graphite in lubricants and in pencils, and then diamonds, of course, everyone knows diamonds are commonly found in jewelry, especially in wedding rings. But they also have other important functions. And then these Fuller rings and Buckminster balls are used as semiconductors and other things that as time goes on, we're finding more and more uses for them. All right. But if you look at these diagrams very closely, you can see that each one of these carbon allotropes have different structures, but they are solids. Here is a table for each one of these 3 carbon allotropes that you need to write down in your table in your notes and become very familiar with these ideas. I will quiz you on them. IB and AP will test you on these ideas. So unfortunately, you're just going to have to memorize them. All right. So really quickly, some highlights there as far as graphite is concerned is that for the AP and HL students, you really should make note that that you have sp2 hybridized orbitals or hybridization going on with graphite. They form hexagonals, parallel layers that form angles of 120 degrees, and the layers are held together by weak van der Waals forces. And if you go back to look at our diagram here, you will see the hexagonal layers here, and each one of these points represents a carbon atom. And then you have each layer is going to be held together by a weak intermolecular force called the van der Waals force. We'll talk more about van der Waals forces in our next lecture. But you can think of as that each one of those layers of hexagonal structures are held together by a bond called an intermolecular force or a van der Waals force. Right? And those bonds are easily broken, and because they're easily broken right here, graphite is great for pencils, because you write in a layer and it breaks off, and then you start another hexagonal layer and it breaks off, and then you write on another hexagonal layer and so forth. So graphite is great for that. Alright, some things you need to know about graphite too is that graphite does have a little bit of delocalized electrons, and so therefore they are conductors of electricity. And then they are solid, gray solids, they're non-lustrous, and again we talked about that they're used for lubricants and pencils. Alright, let's go to diamonds. Diamonds are sp3 hybridized, covalently bonded, and they're tetrahedral in structure. So graphite are hexagons, whereas diamonds form tetrahedral structure. It is the hardest known substance that we know of. Diamonds are extremely hard. And by the way, these are all covalent networks that we're talking about here. So they are very hard. They all have very high melting points. Diamonds are not good conductors of electricity. They have a lot of luster to them, and they're easily polished because of their luster into jewelry or ornamental stuff. They also are great for tools because of their hardness, machinery for grinding and cutting glass because they are hard. So these are some things you have to look at. If you look at the diagram here, you can see that diamond structure is definitely in a tetrahedral arrangement. You can see one there, an atom, carbon, 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 and you got this tetrahedral structure. So you can kind of look at a carbon, 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 and carbon. So diamonds have that tetrahedral. Alright, so a fullerene, or these buckyballs, they're also covalent networks. They have sp2 hybridization, and they're bonded in a sphere of carbon atoms, and there's usually about 60 carbon atoms in that spherical structure, and they consist of 12 pentagons or 20 hexagons. And so you can look at it, it almost looks like a soccer ball in a sort of way, where you can see from this picture you got carbon, 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 and carbon, and they form these hexagon structures here, and also pentagon structure, which is sort of, I guess this is more pentagon. The hexagons are kind of next to it. So between pentagons and hexagons, there's a hexagon right there. Right. So it's made up of pentagons and hexagons that form this spherical round ball. It looks like a soccer ball again, and it has 60 carbons in it. So, and I think what you should do is think about or memorize that they have 12 pentagons and 20 hexagons that make up that structure. Let's see. As far as looking at some of the properties here, they do have a little bit of delocalized electrons, and so they are considered semiconductors. And they form yellow crystal solids. They're soluble in benzene. They react really well with potassium to make superconducting crystal materials and so forth. So just kind of have an idea of this table and the special properties and characteristics about each one of these types of carbon, elemental carbon structures. Alright, another covalent network compound we want to look at is silicon. Silicon, just like other covalent networks, they're very hard, and they have very high melting points. Silicon also is a semiconductor itself. As far as the structure goes, they're tetrahedrals, and basically you're going to have, as it shows kind of in this structure or this model here, you're going to have a silicon, and then you're going to have another silicon bonded to another silicon, and another one, forming these tetrahedral. And of course the tetrahedral angles are about 109.5 degrees, just like other tetrahedral structures. So with that, though, those tetrahedrals are just arranged in these big, long, repeating crystal structures that create like glass and sand and so forth. So super strong bonds, super hard, and again, high melting points. All right. As far as a covalent network that's similar to silicon, that would be something like silicon dioxide. Silicon dioxide has a formula of SO2, and silicon dioxide is essentially really glass and sand. We often refer to it as quartz or silica. The structural bonding you'll need to know. So each of the silicon atoms are covalently bonded to 4 oxygens, and that will create a tetrahedral structure. So you can think of this as silicon, and you have one oxygen, another oxygen, and another oxygen, and another oxygen, forming that tetrahedral or a silicon tetraoxide type of arrangement. All right, but the ratio is still, oops, I forgot the I there. The ratio is still 1 silicon to 2 oxygens, because as you look further, even though each silicon is covalently bonded to 4 oxygens, the oxygens is combined. Each oxygen is combined or bonded to 2 silicon atoms. All right. So keep that in mind for silicon dioxide. As far as properties of silicon dioxide, again, they're strong structures, insoluble in water, have very high melting points. They do not conduct electricity or heat. And so you can think of them in those terms. Alright, so that's it for these giant covalent network molecules. We'll discuss them a little bit more when we talked about some physical properties of compounds, with their melting points and boiling points and other characteristics later on here. Alright, so just get familiar with this, review these lecture notes, ready for the quiz and so forth. And that is it for this.